Okay, so last time we have started to talk about the PN junction current. So we have been go through the how can we use this the concept related to the excess carriers. So last time we have been already mentioned that since this excess electrons exist in the neutral p region, and also the excess holes exist in the n region. So therefore, we have to consider the concept related to the quasi-Fermi level, and therefore we have this formula. The total hole concentration can be considered as a P0 plus this excess hole carrier, which can be expressed by this with considering the quasi-Fermi level. And similarly, the total electrons can be considered as a quasi-Fermi level as shown here. And because of the carrier concentration are exponential function of distance, and therefore the quasi-Fermi level are linear function of distance as shown here. This is because we have an exponential decay here, and therefore by plotting under the consideration of Venn diagram, that would be the linear function. So we will continue to move on to understand what would be the formation, how the formation of the PN junction current here. So at the space charge at the x equal to xn, and also under the low level injection condition, therefore our n0 times the Pn xn is equal to the n0, because now this is a Pn xn at the x equal to xn location, so we can just put this one into here. Therefore Pn 0 exponential VA over VT and because of n0, Pn0 is equal to Ni squared, and therefore this equation can be rewritten as Ni squared exponential VA over VT here. And because of the difference in the quasi-Fermi level is related to the applied bias of the VA, and therefore N0 P is equal to Ni squared exponential EFN minus EFP over KT. Because this term is equal to this one. The difference between the EF and EFP is nearly constant through the depletion region. As shown in the last slide. So the difference in here is nearly constant across the depletion region. So the total current in the junction now is the sum of the electrons, individual electron and whole current. So if we want to estimate the total current, actually, which is equal to the sum of the electron and whole current, and also that are constant through the depletion region. So therefore, the idea is that because the current here is constant in the depletion region, so therefore we are able to estimate the total current by consider the total, the sum of the electron and whole current in the depletion region. So that's why the current here, for sure will be equal to the current here, and the current here will be equal to this plus this one. So that's the ideas. So that's the idea that in there, how do we estimate the total PN junction current? Since the electron hole current on continuous function through the PN junction, the total PN junction current will be the minority hole diffusion current, minority carrier hole diffusion current at x equal to xn, which is this one, plus the minority carrier electron diffusion current at x equal to xp, which is this one. So consider the minority carrier diffusion current, the equation here. So we have the equation as shown me here one, and therefore can be also expressed as here. And we consider the uniform dope, the thermal equilibrium carrier concentration is constant. So therefore, we will start to use this diffusion current to estimate the total current. So the next day is we just try to put all the equation we have been known in calculating the diffusion current. So the whole current density for this forward bias condition in the x directions can be expressed as shown me here. The JPXN is equal to E dp Pn0 LP exponential EVA over KT minus 1. So similarly, we can get the Jn at minus xp. So we have this equation, and therefore the Jn at minus xn is equal to E dn N P0 Ln and exponential EVA over KT minus 1. And therefore, the total current density in the PN junction, as I already said, which is the summation of the current at here plus here. So in the end, the total, the current equation is shown like this one. And to simplify this equation, normally we will define this term as a constant, which is this one. We can define this one as a Js. Where the Js is equal to E dp Pn0 LP plus EDN NP0 Ln. So we can have this constant as a Js to represent this equation, because in this equation all the parameters are related to the initial and without any voltage dependency. So also from this equation we can realize that our current, our total PN junction current J is proportional to exponential EVA over KT minus 1. So therefore we can expect the current is a certain exponential correlated with our forward bias, where we apply the voltage on the anode side. So with this equation, finally we can expect our current relationship, the current versus voltage relationship in the PN junction, which is JA, the current in the anode side, versus the applied voltage in the anode side, which has this kind of a characteristic because of the current is proportional to exponential EVA KT or minus 1. And therefore, we have some further discussion on this ideal PN junction current characteristic. So since we have been derived the current has such correlation, and also we have shown the Js is related to this term, and the ideal diode equation, which can be shown as here. And particularly, this Js has a particular name is referred to as a reverse saturation current density, and therefore if you plot the full IV characteristic with considering not only the first quadrant, the first quadrant will be the turn on, the fully turn on, so which has a characteristic as shown like this one, where J is equal to Js exponential EVA KT minus 1. On the other hand, the Js also refer to the, as shown here, is a reverse saturation current density, and therefore the Js is shown in here. Under the reverse bias, we have the reverse saturation current density, Js. And of course, the Js, the reverse current cannot be continue flat, because once we switch to the very high reverse voltage, we will start to see the breakdown happen. So that's the breakdown. And therefore, this is our full IV characteristic for one ideal diode. We consider the first quadrant and then the third quadrant of the forward and reverse bias. So here is a summary of physics. When we have a forward bias being applied to a PN junction, the forward bias voltage will lower the potential barriers, so electrons and holes are injected across the space charge region. The injected carrier become minor carrier, which then diffuse from the junction and recombine with the majority carrier. So under the forward bias, we will start to see the barriers between the P and N is getting lower, and therefore the electron will start be able to diffuse to the left hand side, and then the hole will start being able to inject to the right hand side. But once reach to the right hand side, that becomes a minority carrier, and then the electrons once reach to this side, that will become as a minor carrier, and therefore we have to use the same concept we have learned from the excess carriers. We consider the excess carriers, we always see the minor carrier diffusion current decays exponentially in each region, but the total current still remain the same, and therefore we can take this advantage to estimate the total current by consider the current here plus the current here, and that will be equal to our total current here. And so because we have a minority carrier current here, so therefore the majority carrier current will be the total current, just minus this one. So we can also in the end to get it as a majority carrier current. So the idea is, first of all, we try to find a way to estimate the current here and current here, and therefore the total current will be equal to 1 plus 2. That's our third state. So because the current is constant in the whole system, so once we can have the current here, then we can start to have the current here, and therefore the majority carrier current will be just the total current minus minority current. So in the end, we can also get this majority carrier whole current on the P side and majority carrier electron current on the N side. So the idea is not that very complicated. But of course, the process to be stay one by one to continue until so far. The equation, if you look at the equation side, yes, it's indeed a little bit complicated. But if you try to be a patient to go through the whole process, in the end, the physics is quite straightforward. Okay, so we have some additional concept we will discuss here. One is a generation, recombination current, and a high injection level. Because right now in the previous parts, we all talk about ideal case. We only talk about the low level injection, but in the reality, there's a chance to have this recombination because we have this excess electron and holes, and then the excess electron and holes will have the chance to recombine, and therefore we have to take into account this recombination, where we can consider this very classical Schottky reed hole recombination series can be shown in here, and therefore we can start to have this reverse bias generation current. The mobile electron holes have essentially been swept out of the space charge region, and therefore the carriers will be equal to 0, and we consider this recombination. The negative side implies a negative recombination rate and generating electrons hole pair with within the reverse bias space charge region. So in the end, is that under reverse bias, the electrons and hole will be swept out from the space charge region, but we have to, at this moment, we can start to have this recombination that will generate the electron hole pairs under this reverse bias space charge region. So that's a certain concept that we have to pay attention. So as electron holes are generated, they are swept out of the space charge region by the electric field, and the flow of charge is in the direction of a reverse bias current, and therefore this reverse bias generation current is a current in addition to the reverse bias saturation current. So in the previous IV characteristic, we have been shown in the previous IV characteristic, we have shown the forward will be like this way, but reverse we have the one constant Js. But if we take into account this additional generation current, and therefore we will see in reality the reverse bias always get a higher current than this pure reverse saturation current, and this difference is mainly due to this additional reverse generation current. So, also, under forward bias, electron and holes are injected. Electron and holes are injected across the space charge region, and some excess carriers in the space charge region, and some of these electron and holes will recombine. So, under forward bias, now we can understand the holes will be, the holes can inject it towards the right, and then the electrons also can inject it towards the left. And therefore, there's a chance to have the recombination in this region. And therefore, this recombination will cause this forward bias recombination current. So some of these electron holes will recombine with the space charge region and not become part of a minority carrier distributions. So this is also the one of the curve showing that this related recombination rate which will be a high recombination rate in the space charge region. Therefore, the total forward bias current density in the p-n junction is the sum of the recombination and ideal diffusion current density. So under the forward bias, we also have to take into account the impact coming from recombination, and therefore the total forward bias is not only the diffusion current, but also we have to consider this recombination current. So in the end, with all taking into account these non-ideal factor, therefore we have to do a little bit revise on our forward current here. So this is ideal diffusion current, but now we have this recombination current, which is here. And therefore, the total current, which will be the sum of this one, and therefore we will get this curve. And this is when we consider the recombination under the low injection. And therefore, to reflect this characteristic, we put as the n factor in this equation, where we call this as the ideality factor. So we can have this ideality factor, try to see how this our forward current will be influenced by this non-ideal effect. If this is all as diffusion current dominate, we should have this ideality factor around 1. But if we will be influenced by recombination, then we will see this will be revised as a 2. So if you look at the many literature who study the diode, they always report this ideality factor because this reflects that the transport characteristic is purely dominated by diffusion of something else. If you get a more large N factor, that means that you actually will be influenced by more non-ideal effects. So the last one, the high-level injections, that we should also mention, because in the previous part we always assume this is under the low-level injection, but in reality we have this high-level injection. So as a forward bias voltage increase, the excess carrier concentration increase and may become comparable or even larger than the majority carrier concentration. So this idea is, if we have this one p-n junction, P and N here. So as we know that we apply the forward bias, so we can start to see we will have the whole injections toward the right. And we will foresee the electron injections toward the left. If you consider the background doping of this P and N is P0, and also the N0 here. So if the injected carriers larger than the background doping, and therefore this is a case we call as a high-level injection. So this is a case where our Pn can larger than N0. So once we have a whole injection, so we should have the Pn, and once we have electron injections, we should have the Np here. So therefore, if the Pn is larger than N0 and Np larger than P0, so this is a case where we have the high-level injection. And now we are going to show how actually this high-level injection can influence our IV characteristic. So we're starting from the basic, where we have been shown the Np is equal to Ni squared exponential Va over Vt. But now we have to consider there's excess carrier delta N and delta P here. And now the delta N is larger than N0. The delta P is larger than P0. So because right now this is larger than this one, this is larger than this one, so we can do a approximation, show me here. This term will be mainly dominate as a delta n times delta p, which still roughly equal to this equation, ni squared exponential VA over Vt. But now if we consider the excess electron is equal to the excess holes here, so therefore we can have this equation where we have the 2 in here, and therefore the current equation must be proportional to exponential VA over 2Vt. So based on this current equation, we can foresee our current IV characteristic will be shown as here. So ideally we have the one ideal, right? And under the low bias we need to consider the recombination, which is here. And in the middle we have the ideal case. But once we apply the high forward bias, we will start to expect to see this high level injection, and therefore we will start to see the current is become flat again. This is because exponential VA over 2Vt. So because we have the 2 in the here, so therefore this will limit the performance. Under high carrier operation, under the high current operation. Because ideally we want to have as higher current as possible, so we always expect it to show me here. But in reality, because due to this non-ideal high-level injection, the slope will be changed. So therefore, we will see the current will decrease and then getting increase, become slower and slower, because this is due to this high-level injection. Okay, so finally we complete the first device that we have been discussed for the PN diode, and next we will start to move on another very important, which is not exactly the device, but it's a very important interface that's related to the metal and semiconductor. Because of this interface, this junction of the metal semiconductor, that also will highly influence our IV characteristics. So in general, we will see this metal semiconductor that can already observe in our MOSFET structure. So if you look at the MOSFET structure, so this is our dielectric, and then we have this gate metal. This is a very simplified schematic that where we have been drawn previously. We have a gate, source, drain, and also the dielectric. But in reality, we also need to have the metal in this region and metal in this region, because this is region that we want to apply the bias. So we will apply the VD and we will sense the current. And for the source, in most of the case, we will ground it as shown here. But anyhow, we need to have the metal deposit as an electrode on top of the source drain. And therefore, this interface is the metal semiconductor junction. And in general, there are two different types of this junction. The first one is we can have the ohmic junction. And the second one, we can have the Schottky junction. So the basic difference is not only for sure the physics between the Schottky and ohmic for sure different, but the most important is influence the IV characteristic. So the expected IV for Schottky and ohmic is shown here. So the ohmic junction means that the IV characteristic follows the ohmic law, which means we have the linear characteristic between the current and voltage. And the most important, this IV characteristic will definitely go across the 0 point here. So this is a typical characteristic for the ohmic junction that generally follows the ohmic's law. And therefore, so this is an ohmic junction. And on the other hand, the Schottky junction actually will not work as the ohmic law. The Schottky junction has a rectifying characteristic, which means under the forward bias, we need to apply a little bit voltage larger than the forward turn-on voltage, and in the end start to have the current increasing. So this is our VF. And under reverse bias, there's no current until the breakdown. So this is a typical for the Schottky junction. So here is what we expect to learn here. So explain the Schottky junction formation. That's a very important. Why, how the formation of the Schottky junction, and analyze the band diagram, and also understand the difference mechanism between the Schottky and Ohmic contact. And because once we have this metal semiconductor junction and the current transport from this metal semiconductor is very important. So need to understand the general case, for example, the thermonic emission and also the tunneling here. And finally, it's under some non-ideal effect. For example, we have this barrier lowering and we have this Fermi-level pinning. That all will in the end influence our metal and semiconductor characteristic. So the first one is to understand the Schottky barrier diode here. So why this can be considered the diode? Because we actually, once we have a piece of a semiconductor here, if we have a piece of semiconductor here, and then we put a certain metal on top, so this is a metal, and for example, let's assume we have the N-type semiconductor. But actually, in reality, we will find out that the metal and semiconductor still will form as a depletion region in here. We will still can see the depletion region between the semiconductor and the metal. And that's why we can also consider as a diode, because once you have a depletion region, that means lots of the characteristics are very similar to a PN junction and PN diode. So one of the first practical semiconductor device used in the early 1990s was the metal semiconductor diode, and therefore we need to start to understand. If you want to understand the metal semiconductor, we always starting from the band diagram here. So on the right hand side, we have the N-type semiconductor. And on the left hand side, we have a metal. This is a situation that these two materials that haven't touched on top of each other. So on the right hand side, we have the N-type. So therefore, we can expect our band diagram is shown me here. We have still the conduction band, valence band. Because right now we have the N-type. So that means our Fermi energy must close to the conduction band. That's EF. And that will be above our EFI. And now we have to define the several parameters here. The first one is the semiconductor work function, which is a phi s. Phi s is a semiconductor work function. And also we have this chi, which is known as electron affinity. and we consider as a reference plane in here. We have a reference plane, and then the difference between this reference plane and also the conduction band that we consider as electron affinity. And the difference between this versus the Fermi energy that we consider as phi s. And similarly, we can have this metal wave function with respect to the reference plane. So we consider the metal side, therefore, and also if we consider the Fermi energies here, and therefore the difference between the metal and Fermi energy, which is our phi m. So the phi n is a metal wave function. So based on this band diagram that we have a phi s here and phi m here. So therefore this is a case we consider phi n is larger than phi s. This is a case that whether these two materials not contact yet. But right now, if we try to contact these two materials, we put the metal on top of semiconductor. The first important thing is that the Fermi level become a constant through the system because of this is in the case of a thermal equilibrium. And therefore, this has to align with this one. Because of now this is in the same system, so the Fermi energy must be the constant. So therefore, once these two materials contact with each other, there must be something change. Still the same, we're starting from our EC, EV. And also N time, so therefore the EF is close to EC. But because of the phi n is larger than phi s, and this, if this going to align this one, that means this one has to be completely shift upward. So therefore, the EF of the metal side will be aligned here. This will be the EF on the metal side, and therefore we can start to see the whole, this one will become like here. So we will start to see this one will become like in this way. So therefore, because right now our Fermi level are aligned with each other. And once we see this band bending, that also suggests that this is a depletion region, right? So this is the same one that we see in the PN diode. So that's why I draw here as a depletion region. This is fully aligned with these two. So now we define this one as a phi B. And this one still the same, the building voltage. And also the positive charge donor atom remain in the semiconductor here. So that means we have the lots of the positive charge donors here. Let's create a space charge region. So the same graph is shown me in here. This is same exactly that how I draw in the last slide. So now we can define as several parameter here. So for example, the phi B, which is can be estimated as our metal work function minus our electron affinity, and our VBI, the building voltage, which is our phi B minus the phi N. So now we can start to understand the Schottky barrier's height, which is phi B here, is highly determined by the electron affinity and also the metal work function. So if we consider different semiconductor, that will give us a different electron affinity, and different metal on top of semiconductor will give us a different metal work function. So these all will then influence our Schottky barrier height here. So for sure, the most important is the silicon, and then the very often used metal, aluminum, gold, nickel, PT, and titanium. These are all the metals that we are often use for the semiconductor. So now we have to consider in the case where we apply, in the previous case it's under the without any applied bias, but for the operation of this Schottky barrier die, for sure that we need to consider under forward bias and the reverse bias. So when we apply the positive bias to a semiconductor with respect to the metal,
the semiconductor to metal barrier height increase, while phi b remains constant in the ideal case. This bias condition is what we consider as a reverse bias. And therefore, now we have to try to draw the band diagram under the reverse bias. So this is n-type semiconductor. Now we apply the reverse bias. And therefore, the Fermi energy is not a constant in the whole system. There's a difference for the Fermi energy between the semiconductor and the metal. So this is EF in the semiconductor, and the difference between the EF in semiconductor and then the metal. This is the EF in the metal. This is EF in the metal. So the EF between the metal and semiconductor here is due to additional reverse bias. And therefore, with this additional bias, we can foresee our barrier height can be increased. So this still our Q5B, but now this one become the QVBI plus VR. So this is case under the reverse bias case. And similarly, we can quickly draw the band diagram under the forward bias. So under the forward bias, actually we will start to pull down the Fermi energy here. So therefore, this is our metal Fermi energy, EF. And therefore and then the difference between these two is a VA. And therefore, we can see the band diagram will become and this will become as a QVBI minus VA. So once positive voltage applied to a metal with respect to semiconductor, the semiconductor to metal barriers, VBI is reduced. Because once it's reduced, the electrons can more easily flow from the semiconductor into metal since the barrier is reduced. So, if you understand the analysis of the PN junction, so this should be no problem for everyone because it's the same analysis. We just replace as a 1 P-type junction as a metal, and then but we still need to take into account the metal work function. But if you know the main concept is that the Fermi energy will be aligned or not aligned with the bias, and then it will be very easy to draw this Venn diagram. So now we will still go back to the same analysis that we have in the PN diode. So we'll start to try to analyze these junction properties, and we're based on the same way we do for the PN junction. We're starting from this typical equation, which is our dE over dx is equal to the rho x over x zone s. So therefore, to analyze the electric field, we do the integration of this one So we do this integration of this one, we get this term. The electric field is 0 at the space charge age in the semiconductor, and therefore we can start to have a C1, and electric field can be estimated as shown here. And the space charge width W here may be calculated as we do for the PN junction. The result is identical to as what we already shown previously as a one-sided PN junction. So in the previous case, we have been talking about this a special case called the one-sided PN junction. So the one-sided PN junction is a case where we have the typical P but with a highly doped N++, and therefore the depletion region of this one-sided PN junction here, W, can be considered as a WP because of the majority of the depletion width will happen in the P region. That's what we call the one-sided PN junction. And this is the same case where we analysis as metal and semiconductor. Now we have this P here, but now we put as a metal, which we have a metal here, and then you can consider as a metal is a highly doped material, so it's exactly has the same kind of a phenomenon that we put the N++. And also there's no chance to have the depletion width in the metal. So therefore your depletion width will be mainly existed in the P region. So therefore in this case the W is still equal to WP. So that's why we can consider this is same and then identical to the one-sided PN junction. So therefore we don't have to prove it the equation again. So we just borrow equation where W is equal to Xn And this is a consideration of the N-type, which has this where we have the ND here. Metal. So here is one example just for your practice. Determine the theoretical barrier height, the built-in potential barrier, and the maximum electric field in the metal semiconductor diode for zero applied bias, and consider the contact between the tungsten and N-type semiconductor silicon dope at a certain doping concentration here. So the calculation is very simple. We just put whatever we know for equation. We have the phi m for our tungsten. This is a tungsten, which is 4.55 volt. And we have electron affinity for silicon, which is 4.01 volt. And therefore the barrier height which is equal to phi m tungsten minus electron affinity, and then which is a 4.55 volt minus 4.01 volt, 0.54 volt here. And now we have to calculate the phi n. KT over Q, natural log NC ND, and then we have a 0.0 natural log uh 2.8 times 10 to 19 over 10 to 16. In the end, we have a 0. Volt here. So the first question is a built-in potential barrier. So that's a VBI, which is a phi B B0 minus phi n. It's a 0. And then the space charge width at the 0 bias. Xn is equal to this one, 2 exon S VBI END. And therefore the maximum E field is E max. END XN exon S, which is 3.21 10 to 4 volt per centimeter. So we have the VBI here, VBI here, and maximum electric field. This example is in response to lots of you, actually not lots of you, probably around 30% of the 40% you, for your feedback and suggestion for this course and request to see whether I can spend more time to teach you how to solve the question. But you can see this question is nothing to teach, just put the equation in, right? And then in the end, everyone just keep writing, noting, and you don't have time to think. So I still believe that the main the part that I want to focus on in this class is the physics rather than spend lots of time to derive equation or solve the equation, because this is just one example that just teaching of this solving equation is nothing help us to understand the physics behind. You just get used to become more good at the mathematics, more good at the calculation. So most of our local students in Taiwan, we have been teaching for how to solve the question since the first year. We go to the undergrad elementary school until our college. So I believe that the graduates, for being as a graduate student, for studying the graduate courses, and for being more professional in the future of engineers, should not just focus on to try to how to be better in solving the question. So all these equations, I believe that with your own expertise, you can understand by yourself. So this is just one example that in the end, if I teach a lot of calculation, just put all these bunch equation and put the numbers in, everyone just write it and didn't understand the physics behind. You just get a bunch of the number value, but you don't get the sense of the physics. I still believe the physics will be the one that everyone can remember for the whole life. After this class, 90% of the equation you will forget it. 90% of the calculation you will forget it. I don't remember all this equation, but I will only think in my mind is the physics, how we can use this physics to help us to solve the questions, especially to help us to design, to understand the semiconductor device that we will need for the future. Okay, so we will take a break and we'll come back in 10 minutes later.
刚上次讲说我是它两边的那个
电流
会一样，那但是像我们看到这个，它是随着距离 decay 的，所以它其实这边应该是随距离递增。
对，没错，对啊。可是 overall current 是一样，所以你的 majority current 就是你 total current 减掉买的点就是 majority。
但是我们这边，因为它是，因为我们中间这边在加，它应该是，或者说两边它1跟2电流加起来，它应该是。
就所有等于所有的电流。
对，但是它应该不是 constant， 因为我们看两边都 decay 到很。
没有 constant 是在 depletion region。对 constant 在 depletion region。
所以它本身 exponential 它是要修正。
对，没有 exponential 是在它会 exponential 的原因是因为它到了另外一个区间之后，它开始会有多数这个是多余的载子。
对。
多余载子在这个地方之后，它就会开始 exponential 的 decay，但它在 depletion region 里面是不会。对。
那我不应该就是说像。刚这边 generation 跟 recombination， 就为什么它就是会在 deplete， 就是在 space charge region 里面会自己。
其实主要就是因为有电场，主要是有大电场。对，主要是有电场，所以你会产生一些 electrophore。你可以简单想象的概念就是没有到 implantation 那一块，但是就像 implantation 一样 ，implantation 就是你有电场，电场就会产生 electrophore。对，那只是 implantation 也是一种。additional generation， 对，但只要你有一个电场在，它就会容易产生额外的电子电动，对。
就是。
Okay, so very similar to what we have been do for the PN junction. So we can also analyze the junction capacitance here. So it's a same analysis, and in the end, we can have this equation 1 over C square is equal to 2 VBI plus VR over S on S ND here. So this is actually very useful equation, because by using this equation, if we consider as a one structure where we have the P-type substrate and also the metal and therefore we can use this 1 over C square, to extract NA and also the VBI. Sorry, it should be the ND. So to obtain the building potential barrier, so we can use this way to obtain the building potential barrier VBI, and the slope also will yield the semiconductor doping ND here. So now we'll move on for the Schottky barrier diode. So with some non-ideal effect. The first one, the non-ideal effect is based on the what we discussed is the barrier height, and then the first phenomenon is the Schottky barrier lowering effect. So, this is a Schottky, or sometimes we call the Schottky effect, or the image force induced lowering of the shock of the potential barriers. So the idea is that if you consider junction and metal, so the electron in a dielectric material at a distance x from the metal will create the electrical field. So if now you have a one charge in the junction side, will also create as an image charge in the metal side. This is image charge. And therefore, these two charges will have the create as an electric field. With a distance between the x. So An electron in a dielectric material at a distance x from the metal will create an electric field. The electric field can be determined by the adding image charge E inside the metal. So we have one image charge in the metal and located at the same distance from the interface. And this is actually some ideas that we have learned from the electromagnetic. So if you follow the first few chapters of the electromagnetic, we all talk about how to calculate the electric field. We consider this image charge, and then we consider this equation with the distance of the 2x. In the end, we can have the phi x as shown in here. Where is the potential phi x here? And this in the end will cause the impact on our barrier height. So ideally we have this Schottky barrier height as shown in the left hand figure here. But because of this image force, we'll create the image force here. In the end we have this phi b will influence our barrier. So you can see the barrier here is reduced. That's our delta phi b. So that's why these phenomena is we call as a Schottky barrier lowering effect. So the delta phi here is shown with this one, where E electric field over 4 pi epsilon s. Therefore, from this equation, we can understand as a large electric field applied, this delta phi will increase. So higher electric field, this barrier lowering effect will become serious, and therefore your barrier height is equal to ideal case minus this delta phi. So once you have a higher delta phi, for sure you will have the lower real barrier height between the metal and semiconductor here. And also from the analytical equation, we will find out that in the end, this will also influence our current because of this additional reduce of barrier height also will be correlated with our electric current as well. So therefore, this graph is showing that the influence of this barrier lowering effects on the electric current. So again, if you look at the IV characteristic, so ideally we have this curve, and then once reach to the breakdown. But right now, because consider this barrier lowering effect where our barrier is reduced even larger under the high bias, then we can foresee our lead current is increased. So this dramatically increase is because with this barrier lowering effect. And we will also see the breakdown voltage reduce. So therefore from this graph you can see this is a reverse bias, so it's here, and this one is there, just a little bit upside down. for this figure, but in any way, just try to understand this characteristic. So with a very low effect, we see the current increase. But once we consider as a multiplication, which is actually the average breakdown, the impedance. Then we will see the current will increase the earlier, then shows a lower breakdown voltage. So that's the inference from our this kind of a Schottky barrier lowering effect on our reverse lead current and also the breakdown voltage. So the next issues we want to talk about is the interface states here. So the barrier height of the metal semiconductor junction is determined by both metal wall function, but not only the metal wall function, but also the semiconductor surface. Or interface states. Which is this one. And why do we possible to have this interface state? Because of ideally this is a forbidden band gap, and the forbidden band gap region didn't possible have this allow energy state, but because this is a broken interface between the semiconductor and then another material, so the bonding here will be broken, will be abruptly terminated at this place, and therefore this abruptly terminated surface will start to have lots of allowed energy state at this interface, and this allowed energy state in the interface that we call as an interface state here. So assume that all states below the surface potential phi 0 are donor state. So the donor state by definition is a neutral if a state contains electron, and also the positive charge if a state does not contain the electrons. So assume that all states above phi 0 are accepted. So the state below phi 0 are the donor state, and then the state above the phi 0 are acceptor state. Which by definition the acceptor state is a neutral if the state does not contain electron, or if negative charge if the state contains electrons. So with all this information, that in the end we can have this derived equation. In here we won't show how this derived because it's a little bit complicated. But in any way, you will see there's a term of an interface state density as shown here. So that means these barriers between these ones, that's also influenced by this interface state density. So let's look some of the practical situation. The first one is that if we got a really poor interface, so if we have a very poor interface quality, and then we will have the very large DIT value. So, and therefore you will find out that based on this equation, if we have the very large DIT, then our phi BM is expressed here with respect to the band gap and minus phi 0. But the problem is this is independent of a phi m. Independent of a metal work function and also the electron affinity. So the barrier height is now fixed by the band gap energy and potential barrier, potential phi 0. And therefore the barrier height is totally independent of the metal work function and semiconductor, metal work function and semiconductor electron affinity. The Fermi level becomes pin at this surface. And because of we cannot use the metal work function or different electron affinity start to change this barrier height, and the barrier height will be only related to band gap, and therefore this is what we call the pin. That's a very professional term in the literature. We always call this as a Fermi level pinning. So probably this term is new for you for the first time if you are new to this field, but this non-ideal effects definitely you will face in the future, because for many advanced semiconductors we always face the poor contact, and most of the reason is coming from this Fermi level pinning effect, because our interface just way too poor, because we won't use the pure silicon. We will use those exotic semiconductor materials that always has a very poor interface, and that will cause we got a very poor ohmic contact, and then one of the main reason is this Fermi level pinning effect here. So if we can make our interface as good as possible, and that means our DIT will approach to the 0. So our barrier height can be only depends on the metal work function, which is good because we want to have use a different metal work function to tune our barrier height. In the end, will influence our current transport characteristic. Okay, so that's a typical symbol in here. Just show that this is a bit of a summary for this is a typical metal semiconductor work as a Schottky barrier height, and then the symbol for this Schottky barrier height is shown me here. This is a circuit symbol for this Schottky barrier height, and then if you compare the typical characteristic between the dial here, so now you will see so this is IV characteristic. So we will have the typical Schottky barrier height, Schottky barrier diode with this kind of characteristic. But if we have the very high increase, then the turn-on voltage will increase as well. So that's a typical phenomenon that we will quite often see in the Schottky barrier diode. So we finished the Schottky barrier diode, and now we will move on to the non-rectifying barrier, which is the ohmic contact. So ohmic contact are metal semiconductor contact, but in this case they are not a rectifying contact. And ohmic contact is a low resistance junction. So this is a low resistance junction providing conduction in both directions between the metal and semiconductor. So therefore you can see the current can be flow under the forward bias and reverse bias here. So the first case we will talk about how to understand the Schottky this ohmic contact is where we consider the metal work function smaller than our Schottky semiconductor work function. So still we consider N-type semiconductor. And then this is N-type. So still we have the phi s. And also the electron affinity. But now we consider the case where our phi m smaller than phi s, which means this is our metal Fermi energy, and then our work function is here. So in this case, phi n is smaller than phi s. So once we put these two materials with each other, because right now our Fermi, the phi n is smaller than phi s, right? So this is smaller than this. So this, if this is going to align with this one, this must be a little bit bending toward the downside, and therefore we can see the band become like this one. So this is our phi m, and this is phi n. To achieve thermal equilibrium in this junction, electrons now flow from metal into low energy state in semiconductor, which makes the surface of this semiconductor more N-type. Right? Because of this sentence, means this is getting more n-type because now your Fermi energy is much close to your conduction band, sometimes even above your conduction band. That's kind of like the degenerate. This means that we have very heavily n-type here. So this region become more n-type because now our Fermi energy is pretty close to EC, even above the EC. So, therefore, if you have the n-type semiconductor, you want to make us a good ohmic contact, you definitely have to choose a metal work function should be smaller than semiconductor work function. And similarly, if you want to make the good ohmic contact on the p-type semiconductor, then we have to choose phi A is larger than phi S. So consider p-type semiconductor. Phi S is here. That's our p-type. And now we have to choose the metal that has a phi N larger than phi S. So once we try to put these two materials together, we have the Fermi energy as a constant. So, similarly, with this case, we will find out that at this interface, actually, this is become more p-type because your Fermi energy is close to the EV, even below the EV. So that's why that we are able to make us an ohmic contact, because with this metal wall function condition, we can make the N-type even more N-type as a service, P-type even more P-type as a service, and especially that the carriers, the electron and holes won't see any barriers. So you can see from this case, the holes are here, can easily flow to the metal because they don't see any barriers. And also similarly, the electrons here can flow to the metal, and then these carriers didn't see any barrier. So there's one additional concept that we call the tunneling barrier. The idea is very similar. Just try to look at this with a very highly doping, because the space charge width in the rectifying metal semiconductor contact is inversely proportional to the square root of the semiconductor doping. So, which means your doping concentration increase and then your depletion width is definitely decreased. So the width of depletion region decreases as the doping concentration in the semiconductor increase. Therefore, as the doping concentration increase, the probability of a tunneling through the barrier increase. So then you can see this one, because of these heavily doped, and then you see the barriers here is slightly become thinner, and therefore the carrier here will be much easily for the tunneling. So that's why we call these as a tunneling barriers here. In most of the semiconductor case, we consider as a metal. Actually, we always prefer to make this source, this junction as a highly doped, because normally this is a contact resistance between the metal and junction. So once we have the N++ highly doped, and therefore we always see a good reduction of the contact resistance. And one of the reasons is due to this tunneling barrier. So these are some of the calculation, but the idea is the same. If you look at the loss equation, the ohmic contact RC is proportional to the barrier height. And also inverse proportional to the doping concentration. So therefore, the typical strategy to make it a good contact is always try to reduce the barrier, increase the doping. Then the goal is try to make the contact resistance as smaller as possible. Finally, I will just show you as a knowledge from this chapter is enough for us to understand the certain analysis in the literature. So this is one of the classical paper that published in 1996, and the title is very straightforward: Schottky barrier and contact resistance on the P-type gallium nitride. So from this title, The only things probably you don't know is a p-type gallium nitride, but which is not that important because just a kind of a semiconductor. So the key words talk about the Schottky barrier and contact resistance here. So again, this is a paper published in the Applied Physics later, so they have a different format for the IEEE, but still we can find out that there's an abstract. So in the abstract, we always starting from the abstract. So the first sentence of abstract, we measure the Schottky barrier. We measure the Schottky barrier height and specific contact resistance on the 4 different metals on the p-type gallium nitride. So this is also one of the examples that when we try to write the papers, it's always we try to make this as a very straightforward, very clearly. The first sentence actually just another reference from the title. There's nothing additional information. Only the difference is just they put as some more details that they measure this on the 4 different metals. Because in the first sentence they mention the 4 different metals. So the second sentence must be a little bit more specific. What kind of metal they have been used? So in this study, they studied the barrier height on the PT, nickel, gold, and titanium here. And also, they got the characteristic, the Schottky barrier height with the characteristic of these 4 metals have this characteristic of 0.5 to 0.65 electron volt, and the specific contact resistance is here. So that's actually from the first few sentences, they didn't show too much difficult analysis. They just say they try to measure this on the 4 different metal and they obtain this characteristic. And then the next one, our experimental result proved that the Schottky barrier height and specific contact resistance decrease with increased metal work function as expected theoretically. So this actually is very interesting because this is 1996, but from silicon, the theory of the Schottky barrier height and contact resistance has been already demonstrated like several decades ago. So this paper actually, in the end, they just confirmed the contact resistance decrease with increase of metal work function. That's exactly we learned from this textbook and as expected theoretically. So in the end, you will find out that even you just find something very similar, just like the textbook knowledge, you still have the chance to get some good publication because you just reconfirm again the series works. The series work not only for silicon, the series also work for some other semiconductor material. But if unluckily you find that the series just didn't work, that's still good because you can try to have another publication just to illustrate why the classical series on silicon probably not work on your materials here. So in any way, the abstract is very straightforward and very easy to understand. And also if you look at the conclusion here, in conclusion, we measure the semiconductor Schottky barrier heights of 4 different metal on p-type gallium nitride. So now you see the sentence of this one is exactly the same, right? Of the abstract. So the idea is that always when you finish the conclusion writing, your abstract, to be honest, just refreshing. You use the same logic, refresh the result. So it's the same. So you can see the conclusion is mention the same things. And using the both contact and reverse bias IV will also measure specific contact resistivity. It was found that Schottky barrier height and specific contact resistance decrease with the increase in metal work function. So again, this is the same sentence. same sentence like from the abstract as I mentioned here. So, and the last sentence is that Schottky barrier heights are slightly affected by metal work function. So that's also another conclusion. But anyhow, based on the knowledge you learn from this chapter, is definitely enough for you to understand this literature, because all these keywords are the same keyword we mentioned. But also, you found out actually not that the equation is important to prove the physics, but once we go to this literature, actually those derived equations not that important. It's mainly to understand the physics behind. Okay, so this is abstract. This is a conclusion part, and this is related to the introduction. So this is all whole part is the introduction. So with this all introduction part, that normally this paragraph and this paragraph, if you try to look at a little more details, you will find out this is only the background information. So this only mentions that the 3-5 nitride semiconductor is very important, but recently we face a problem that how to get a good ohmic content p-type gallium nitride, and therefore achievement of the p-type GaN serve as a major breakthrough in the 3-5 nitride semiconductor. This is a time that the people still suffering how to make as a good ohmic content on p-type gallium nitride, and therefore they say that the achievement of the p-type GaN is a breakthrough. At the moment, still this is information related to, at the moment, still try to make us a good p-type gallium nitride. So once they have a good p-type gallium nitride, the next is try to make it how to have a good contact on p-type gallium nitride. So these are all just a background information. So to be honest, we can just skip it, but always important to look at these keywords. On the other hand, or however, so this is the turning point that start to bring you attention that we start to face a problem. The previous the two paragraphs just say the recent advance, but now we got a problem. The problem is the measurement of Schottky barrier height p-type gallium nitride is difficult due to lack of a low resistance ohmic content required in the conventional IV method, which has been a major challenge to clarify the electrical property of a GaN contact. So that's actually serve as a challenge. The main difficulty at this moment, but also which is the motivation of this work. So because of this motivation, finally in this work, we try to systematically measure the Schottky barrier height on 4 different metals by using the certain methods, and so that's the approach. The approach for this work. So we go through this abstract conclusion, a little bit introduction. Even right now you haven't look at the IV category. You actually didn't know what is exactly the details. What's a typical IV? What's a barrier height? How do they do the extraction? You already know what's the key point for this paper. So that will be more efficient for everyone to quickly screen the literature whether it's suitable for you, because then you will understand what's the key points. For sure, there's a lot of some of the more details, but detail is not that difficulty because this just show this the key figure from this figure. So then the left hand side you see the equation. The equation also is exactly very similar to what we have been used in the semiconductor, this textbook, and then the right hand side is a typical IV characteristics. That's with respect to the different metals here, and then use this way to extrapolate the Schottky height. So to understand this paper, to be honest, you probably just need a half hour, like 20 minutes to go through the abstract, introduction, conclusion, and the rest of 10 minutes just look at a certain key figure. Like in this one, the key figure is this figure 1. Okay, so with the rest of time, we still need to move on further. So the next one we will start to talk about is MOSFET. Finally, we move on to the MOSFET. So we will talk about the fundamental for this metal oxide semiconductor field effect transistor, the MOSFET. But when we talk about MOSFET, we just actually try to combine all the pieces we know. We have to know the PN junction, we have to know the contact, we have to know the MOS capacitance. So we actually have divide the MOSFET by the several small parts. But what we have to do this right now is just put all these parts together, and that's just become as a MOSFET. So by the end of this chapter, first we will explain the MOS capacitance operation, and also we'll understand the band diagram and the key parameter, especially the flatband voltage, threshold voltage, and also the analyze MOSFET operation mechanism, and also understand the IV characteristic, especially we are interested in the IDVG and IDVD. And then in the IDVD, there will be the two different regions. One is linear, one is saturation. So we're starting from the heart of the MOSFET, which is a MOS capacitor. So to understand MOSFET, we just look at the most central part, which is the capacitance. So in the capacitance, we have this structure. Still, we have the substrate. And we have the silicon dioxide. And on top of silicon dioxide, we have the gate metal. And then to estimate the capacitance, we normally need to know the dielectric constant of the oxide and then also the thickness of the dielectric. So we need to know the X on oxide and the Tx. So the capacitance can be estimated by dielectric constant over the distance, which is equal to X on R side, X on 0 over Tx. So that's a typical equation for the capacitance of the MOS capacitance. But from this equation, we can already a little bit understand the impact of R side thickness and then the dielectric constants. So if we try to make this R side thickness as thinner as possible, or dielectric constant as larger as possible, so then we will expect we will get higher capacitance value. But why this high capacitance value is crucial for us? Because the current equation, we haven't derived the current, but the current equation is proportional to the mobility, to the capacitance, to the Vg minus Vth squared. So from this equation, current equation, we can realize if somehow we can increase the capacitance, in the end, we can increase the output current. So that's why that we do the scaling, because of if we can make our dielectric thinner, normally we can boost our current. And then for the system as perspective, higher current always brings us a better performance. So that's a goal. Okay, so to understand the two-terminal MOS structure, which is a MOS capacitance, we also will starting from the band diagram. The band diagram is always our good friends to help us to understand. So first one, we will starting from as a case that we have the situation as shown here. This is a case where we apply, and in the middle part is a silicon dioxide. And then we have the dielectric constant and distance here. And now we consider the case which we apply the positive bias on the back side. So this is a positive, this is a negative. So we apply the voltage here because we apply the positive bias on the bottom. So we will have the positive charge here. And also because of this is a negative, so we will have a negative charge here. So in this case, we can consider the accumulation of layer of holes. Because right now we apply the positive here, so we will have this accumulation of holes to the positive charge on the bottom plate of the MOS capacitance here. So that's the first case. And this case is actually this is a typical general that we have the one plate, top plate, bottom plate, and we have the dielectric. So that's a typical capacitance. So capacitance is you have a two metal separate distance, and that's a capacitance here. So this will be similar to the case in our real MOS capacitance, which we have P-type substrate. And on top p-type substrate, we have the dielectric. And then on top dielectric, we have the metal. So now we consider the same case like left hand side. So where we apply the positive here, negative here. Because I apply negative on top, so therefore we have the negative charge here. And you apply the positive here, positive will push the holes, right? So your hole will be try to flow far away the positive bias. And therefore the hole, because we have a dielectric here, so the holes will be accumulated below the dielectric. So the holes in general will be try to push from the substrate to the dielectric, but because of the hole cannot flow into the dielectric, ideally, so therefore the holes will be able to accumulate below the dielectric. So in the end, we will see the holes being accumulated in this region. So that's why we call this as a hole accumulation. So the same phenomenon is that we now apply the reverse bias. We apply the positive bias on top and then the negative bias in the bottom. So if you look at the same case, so now, this is a dielectric and metal. So now if we apply as a positive bias on top and negative bias in the bottom, so you have the positive and negative here. So this will be the charge here will be corresponding to the positive. And remember again, you have a positive charge here, so then you will try to push the hole away. So the hole will try to flow from the surface. The hole will try to flow out from the surface, and therefore you will have the negative charge remaining in the interface. So therefore, you will see this induced space charge region, which has a negative charge here. So if electric field penetrates the semiconductor in the case, majority carrier hole will experience a force away. From the outside semiconductor interface. And as the holes are pushed away from the interface, then a negative space charge region is created. And therefore, this negative charge in the induced diffusion region corresponding to the negative charge on the bottom plate of the MOS capacitor. So now our bottom plate here is negative charge here, and then the top plate is a positive charge. So that's a basic idea that how will be influenced if we have the positive, negative, and how come we have the holes accumulate below the dielectric, how come we have a negative charge below the dielectric. So we will stop here, and then the next week we'll continue to talk about this.